Okay, then we have seen this thing again, just I will repeat. Suppose if I have a fluid flowing in a tube whose cross-section area and the speed of flow is given to us, and we need to figure out the mass flow rate and the volume flow rate. Okay, just a moment. Suppose if I have a tube whose cross-section area is given to us as A, okay, and let's suppose the fluid is moving with a speed V, and we need to know what is going to be the mass flow rate at any cross-section. So suppose if I consider that in a very small time interval in which the fluid will move further by some small amount, suppose if I consider the fluid moves by very small amount, let's suppose it is dx. So the extra volume that is going to pass through, or the volume that is going to be passing through this cross section, we can figure out, no? So that is something I'll write down as d volume, the small amount of volume that is passing through the cross section perpendicular to the cross section, no? Or perpendicular to the area will be A is the area of the cross section and the length is dx. So that will be the volume that passes through, no? And suppose it passes through in time interval dt. So if I'll divide this thing by dt on the other side, what we are going to have is A into dx by dt. And dx by dt, I can write it down as the speed or the velocity that we have got at that particular cross section, which is perpendicular to the area, no? So that is going to be A into V. So the volume flow rate, this is something that we call it as volume flow rate, is going to be A into V. Next, if I want to figure out the mass flow rate, that is also simple only. So if I ask you that what is the amount of mass or what is the mass that is going to pass through the cross section in a very small time interval dt, suppose the length that passes through is dx. So the mass dm is going to be A into the mass dm is going to be the density into the small volume that has passed through it. No? That is, I am writing it down as d volume. So what we have is dm is going to be rho into d volume, and that small volume is A into dx. So now what I need is to figure out the mass flow rate. So I'll divide both the sides by dt, and dt will have rho A dx by dt, so it is going to be rho AV. The mass flow rate is some at any cross section is going to be rho AV, and we denote it sometime with this symbol m dot. Okay. I hope all of you got this thing, mass flow rate and volume flow rate, and we have seen this thing earlier also. It's not like first time I'm telling you this. Okay. Now, next, suppose if I have incompressible flow happening in a tube. Suppose if I have an incompressible fluid and that is passing through, let me draw the figure first. Suppose if I give you a tube and at one end, suppose if I know the area of the cross section here is suppose A1, and the fluid here is entering with velocity suppose V, and the other end, suppose the area of the cross section is suppose A2, and the fluid that is coming out of this cross section is coming out with velocity or speed V2. So here it is entering with V1 and there it is exiting with V2. Now, suppose if I have an incompressible flow established in between. Incompressible flow means fluid are not getting compressed, and also there is no storage of the fluid happening in between. It's not like somewhere the fluids are getting stored. It means suppose if you have a room which is fully packed, like you can't have even an atom space left. And in that case, if you push one person into the room, and suppose the room has got one exit and one entry. Suppose if this room is fully packed, and in case if I push one person here, so whatever will be the and suppose everyone is identical. So pushing one will lead to one getting ejected out of the other end or not. kind of correct. So what I have is, suppose in time dt, the the l- mass that is going to enter here, whatever will be, same must be coming out of the other end, or whatever volume it will enter here, same must be coming out of the other end, if the fluid is incompressible and no storage is happening. So at here, the rate at which the fluid is entering is A1 V1, and at the other end, the rate at which the fluid will be exiting will be A2 V2. So in case if I have an incompressible flow given to us with no storage happening somewhere in between, in that case, I can write down A1 V1 to be equal to A2 V2, or in general also I can write down as A into V will be equal to constant. No? But if you be careful with what V is, it is the velocity at that cross section with which the part fluid moves perpendicular to the area. No? And A is the area of the cross section. So this one, it is also given a name, continuity equation. Okay. I hope all of you got this thing. No? If you want, you can copy. If you can copy in like very less time, or else anyhow, I'm going to share this thing as well. No? Okay. I think I can take a new page now. Okay. Then. Okay. Then next step, we are going to talk about Bernoulli's principle. So we'll see this thing in two different ways. What it is, first I will tell you. Suppose if I'll ask you, tell me what is the unit of P into V's. So pressure will be Newton per meter square, volume will be meter cube. So that is going to be Newton meter. No? It is having same unit as the joules. No? This PV is called the pressure energy. Okay, now why it is and what it is, we'll be seeing this thing later on. Just I'm telling you the name of it. This one I'm going to call it as pressure energy. Okay, so if I'll ask you, what will be the pressure energy per unit volume? So P into volume is pressure energy. So the pressure energy divided by the volume will be our pressure energy per unit volume. So that will be nothing but the pressure itself. Okay. Next, suppose if I ask you that, okay, if for a particle, the kinetic energy I can write down as half mv square. No. So where v is the speed here. Okay, no. Where v is the speed here. There, this v is the capital V. That is our volume. So if I'll ask you what is going to be the kinetic energy per unit volume, so that will be our half m by capital V, which is volume, into V square. So mass by volume is going to be our density. So that will be half rho V square. Similarly, the gravitational potential energy for a particle near the surface of the Earth, or even for an object near the surface of the Earth, what we can do, we can write it down as mgh. But the h there is the height of the center of the mass or center of gravity from the reference level, no? That we know already. So the gravitational potential energy we can write down as mgh. So the gravitational potential energy per unit volume, if I'll ask you, is going to be mgh by volume, and mass by volume will be density, so rho gh. No? So what basically we do in Bernoulli principle, we consider conserving these three energies, which is energy per unit volume at any cross section. So we write down the pressure energy per unit volume, which is pressure itself, plus the kinetic energy per unit volume, which is half rho v square, plus the potential energy per unit volume, which will be rho g h at any cross section will be constant. And just I'll tell you what h is. H is the height of the center of the mass from the reference level. So wherever we decide to have our reference level, that is totally our choice. But once we define that, we must be considering the height of the center of the mass of the cross section from that taken reference level. No? This is something which is Bernoulli's principle. We'll prove it as well. Just I'm telling you the statement here, and also the condition under which we apply. So it is basically based on the conservation of mechanical energy. And here we can conserve, see, when we can conserve mechanical energy, only when we are going to have dissipative forces absent, or the work done by the dissipative forces or non-conservative forces zero. Correct. So, so in case if I have a fluid which is not an ideal fluid, so it's going to apply viscous force, or the force that acts parallel to the surface over which the fluid flows, and that is going to be a non-conservative force. So we need to have a fluid which is going to be an ideal fluid. So for us to be able to apply this Bernoulli principle, the condition is the fluid must be ideal fluid. So once ideal fluid told, it means it is going to be non-viscous. Non-viscous, you understand the meaning of it, that it cannot withstand any kind of forces parallel to the surface. So it cannot apply any forces which will be parallel to the surface. No, and it's going to be incompressible. Next condition is the flow must be a steady flow. We'll see what steady flow means. Okay, no? And it should be a irrotational flow. And what basically rotational flow means, suppose if you have some rotational flow happening, in case if you put a paper which can float on the water, it will start spinning or rotating instead of moving in a certain direction. So it is going to be applicable under the case when we have steady flow of an ideal fluid, and it is going to be irrotational flow as well. And once we consider ideal fluid, it means it is going to be non-viscous and it's going to be incompressible as well. Can you cover this thing? So we'll see what steady flow means. Steady flow is not something which is going to be coming in this chapter. It is a general term that we can apply it even for the flow of something else, maybe flow of charges also, maybe flow of heat also. Okay. And that we are going to do even. Copy this thing. I'll give you a minute. Okay, I can take a new page now. Okay. So to prove this Bernoulli principle, what I will do, suppose if I consider an incompressible flow is happening in a tube and the fluid is an ideal fluid. And suppose at this cross section, which is of cross sectional area, I'll take it as suppose A1, the fluid here is entering at velocity V1, suppose. And at the other end, suppose the fluid is exiting with velocity, suppose V2. Now what I will do, I will select some reference point. Suppose if I select this reference point. Now what I have is, if I consider a very small time interval, and what we find, first of all, the flow is happening for an ideal fluid, which is incompressible in nature, and the fluid is fully packed in there. And so for the flow to be getting established, there must be some work done by the surrounding or no. Correct. Suppose if I consider a fluid flowing because of some pump pushing that fluid into that pipe. So what basically happens at the end of the one end where the pump is doing its job, it will be pushing the fluid particles which are next to the pump. And those fluid particles will be pushing the fluid particles which are next to it and then next to it. And this is how a flow is established. You're getting the point here? What I'm trying to tell here, the fluid particles which are just next to the pump. However, the pump may be whatever may be the way the pump is working. So it will be applying some force onto the fluid particles which are adjacent to it. And those fluid particles will be pushing the fluid particles which comes next to them. And then those again will push the next to them. Like that, the flow will be getting established. So suppose in very small time interval, so what we want to do is to figure out what is the net work done by the surrounding here. And since here we are not talking about some particle, correct? Here we are talking about a system where we have some flow is happening. No? So if I consider this section of the tube, and if I consider this as our system, then work done by the surrounding will be whatever is not in the system. No? So surrounding is doing work. One is gravity doing work. Other is the pressure forces that are there at the end. Maybe I'll name it as well. Whatever pressure forces that is acting at the end A, and whatever pressure forces are acting at the end B. So suppose if I am going to consider a very small time interval in which a dx length of the fluid is pushed into the pipe, or dx1 length of the fluid is pushed into the pipe from one end, and in the same time, suppose dx2 length of the fluid is pushed out of the pipe from the other end. So whatever work is being done will be done on this chunk of the fluid that is pushed in, and this chunk of the fluid that is going to be pushed out. So suppose the pressure that I have got at section A is P1. So the force that will be exerted by the surrounding will be P1 into A1. Here the area of the cross section, I'm considering it is A1, and the area of the cross section that I'm considering here is A2. And what we write down the work done as. So the work done is going to be written as F dot dr, no, or F dot delta R, where delta R is the displacement of the point of application of the force. And here the point of application of the force will be pushed by or will be moved by an amount dx1. So the work done here at the entry W1, if I write down, is going to be P1A1 dx1, since the displacement happened in this direction only. But at the other end, if you will see, the pressure forces will be acting like that. No, P2. What pressure forces? The one that is applied by the surrounding, not the one that is applied on the surrounding. So it is going to be P2 into A2. But you will find the displacement here happens opposite, which is dx2. So the work done here, W2, if I write down, is going to be minus of P2 A2 dx2. So what all things are doing work here is this pressure forces, and remaining is the work done by the gravity. And we know work done by the gravity will be equal to the change in the negative of the change in the gravitational potential energy. But before that, to come to tell you anything further, I'll talk about something which is steady flow. What steady flow is, Suppose if I have got a flow established in some tube, okay, then if I'm going to measure the velocity or the kinetic energy or temperature or density or pressure, anything which has to do with the properties of the flow or which are the properties of the flow at this cross section or at this cross section, it may change if I change my position. Or even suppose if I stay at the same cross section, but I take the reading at different instant of time. So in that case, also we can say that the properties of the flow, it can be temperature, velocity, whatever it can change with respect to time also. So what we can say in general, the properties of the flow, for example, velocity, pressure, temperature, density, etc., is a function of position and time. But in case if you are given that the flow is steady, then what it means that if I fix my position, then whatever may be the property of the flow should not change with time. So it is okay for the properties of the flow to change with position in steady flow, but it must not change with respect to time once we fix the position. Okay, that is what it means by steady flow. Steady flow means the properties of the flow must not change with respect to time if position is fixed. So if suppose if you stay at the same position, then whatever measurements you will be doing for the properties of the flow should not be changing with time. It can change if you change position, it's okay, but it must not change with respect to time once the position is fixed. So since I am applying this thing, whatever flow that we have considered here is a steady flow, then even the gravitational potential energy at any particular fixed position will not be changing with time. So what you will find, the gravitational potential energy changes just because a fluid element is pushed in here and the fluid element that comes out now. The change in the gravitational potential energy happens just for this two person or not, the one that is pushed in and the one that is pushed out. And also, whatever other particles are there in between, their speeds are not changing with time at whatever they are present in any cross section. So for the particles that are in between this cross section will not be having any change in the kinetic energy. The change only happens because of the one that is pushed in and the one that is pushed out. No? So the change in the kinetic energy decay, if I write down, so what we have is the one that is going to be pushed out is having, so whatever mass that enters, same mass must be going out as well or not. So what is the change in the kinetic energy will be half dm v2 square minus of half dm v1 square. Next, change in the gravitational potential energy, if I consider, suppose the center of the mass of the cross section at end A is at height h1. The center of the mass at the cross section B from the reference level is at height h2. Change in the gravitational potential energy will be dmgh2 minus of dmgh1. Next, what we are going to do is to write down total work done. That will be the work done by the external sources, which is the pressure forces, plus work done by the gravity. All together will be equal to change in kinetic energy. And work done by the gravity, we can write down as negative of the change in the potential energy. So what we have, net work done by the external agency will be equal to du plus dk. And net work done by the external agency will be sum of the work done W1 and W2. So if I write down that, it will be P1A1 dx1 minus of P2A2 dx2 equals half dm V2 square minus of half dm V1 square plus of dm gh2 minus of dm gh1. Correct. Next, what you do, you write down dm I can write down as rho a1 dx1, and even I can write down as rho a2 dx2, since a1 dx1 will be same as a2 dx2. So what I do, if I divide throughout this expression with the a1 dx1 or by a2 dx2. Suppose if I divide this entire equation that we have got with a1 dx1 or a2 dx2, since both are same, what you are going to get is, and if I replace dm with rho a1 dx1 or rho a2 dx2, what you are going to find is it will become p1 minus p2 equals to half rho v2 square minus of half rho v1 square plus rho gh2 minus of rho gh1, and simplifying it, it will become p1 plus half rho v1 square plus rho gh1 equals p2 plus half rho v2 square plus rho gh2. So that is something that we have proven, the sum of p and half rho v square plus rho gh to be same at two arbitrarily chosen cross sections A and B. So that is going to be true for any two cross sections that we are going to choose. So that's why we can write down p plus half rho v square plus rho gh will be equal to constant at any cross section. So I hope all of you understood what a steady flow is. Correct? No? Steady flow is not just going to be applicable or will be coming in this chapter. It is also going to be same thing we can apply for flow of heat also, flow of charges also. Steady flow means whatever property of the flow, just you name it, must not be changing with respect to time once we have fixed our position. Okay. All of you understood this thing, that proof of this Bernoulli's principle. There's one more way to prove this thing, but this is enough. And you can look at this Bernoulli equation in different manner also. That PV is a form of energy, which is called pressure energy. What, from where it comes? You check out. That is the energy that comes because of the work that is being done on the system to maintain the flow. No? See, what is the work done by the pressure here is P1 A1 dx1. So if I divide this thing with dt, that will be rate of work done by the pressure here. So just to consider this one as pressure energy, this one as the kinetic energy per unit volume, this one as the gravitational potential energy per unit volume that we are conserving at any cross section. Okay, if you want to copy this thing. Steady flow thing you must copy. That derivation, same exact thing you can find in our book also. Okay. Just copy the steady flow definition and leave a page for the derivation that you can copy later on. Okay, I can take a new page now. Okay. Next, we are going to see something that I'll give the name as speed of efflux. Suppose if I have a tank which is filled with water up to height h, suppose, or maybe any fluid which is an ideal fluid, this filled up to height h. And what we have done, we have made an opening at the bottommost point, and suppose the area of the cross section of the tank is, let's suppose it is A1. And the area of the opening that we have made, it is suppose A2. So, and the fluid that we have filled in here, it is suppose of density rho, and the height up to which we have filled it, it is suppose up to height h. And the moment we open this opening, which is of area of the cross section A2, the water or that fluid will be coming out of that opening with some speed. So with whatever speed it comes out of that opening, that speed is called speed of efflux, and that we can determine using Bernoulli's principle. So since water, suppose if I consider the velocity with which the water comes out of this opening is suppose V2, so the water level must be also falling or not. Suppose it is falling with the rate V1, or the speed with which it is coming down is V1 at that particular instant when the height of the free surface is h. And here you can have two cases arising. Either the top surface of the water tank or the free surface of the water may be exposed to the open atmosphere or maybe not. So in general, if I'll do, suppose the pressure at the just above the free surface of the water, I'll call it as pressure as PT, maybe pressure at the top. And the place where this water is coming out of this opening, just outside the opening I'm considering, it is exposed to the atmosphere. So at this cross section, our pressure is going to be, so what I'll do, I'll consider one cross section here. And at this cross section, it is open to the atmosphere. So here pressure is going to be P naught. Okay. So to apply Bernoulli principle, we must select two cross sections first. So first cross section that I will select here will be this free surface, that is suppose cross section 1. The next cross section that I select is the cross section of the jet just outside the opening, this cross section 2. And at cross section 1, what we have, the pressure is our PT, the velocity with which the fluid moves is Vt, so, suppose V1. And next, we must consider some reference level. No? So what I will do, wherever this opening that we have made here, if I consider that as the reference, that opening not very large, so I can consider the height h to be the height of, so what I'll do here is I'll take this one as the reference for writing down the gravitational potential energy. So the height of the cross section A1 is going to be h, and the height of this cross section is going to be 0. So for the cross section 1 and 2, if I apply the Bernoulli principle, we are going to have pressure at 1 is PT, density everywhere same since incompressible fluid, and the speed is V1, so half rho V1 square. Its height from the reference point is h, so rho GH equals pressure at the other end, it is P naught at the other cross section. Speed is V2, so half rho V2 square, but the height is 0, so that will not be written, that is 0. That is our equation number 1. And the things that we don't know here is, we don't know V1, we don't know V2, no? Correct. So we need one more equation. So that will come from the continuity equation, since we can apply Bernoulli for an ideal fluid. An ideal fluid is going to be an incompressible fluid. So A1 V1 must be equal to A2 V2. That will be our equation number 2. Since I want to find V2, so I will replace V1 in terms of V2 in equation number 1. A2 by A1 into V2. And that I am going to place it in the wherever V1 we find. So what we get is PT plus half rho A2 square by A1 square V2 square plus rho GH equals to P naught plus half rho V2 square. To just simplify this thing and find the value of the V2, what we get is PT minus P naught plus rho GH equals to half rho V2 square into 1 minus A2 square by A1 square, no? So V2 is going to be equal to twice of PT minus P naught plus twice of rho GH by rho 1 minus A2 square by A1 square root over. This is what we are going to have, this velocity of E flux in general. Now we are going to take some cases. Suppose if I have the case that is going to be the most general case when the tank is or the cross section A1 that is exposed to the atmosphere, or the tank is open to the atmosphere. The tank is open to the atmosphere, then the pressure that we are going to have, PT, will be equal to P naught. So in that case, the speed of E flux that I'm going to write down as VE, suppose. So that VE is going to become, you see that rho GH, sorry, rho will get cancelled. We'll have 2GH divided by 1 minus A2 square by A1 square root over. Okay. This is what we are going to have in general. Now, another case is, suppose if it is told to us that area A2 is very, very smaller than A1, then A2 by A1 is going to be very, very smaller than 1. So A2 by A1 square is going to be nearly equal to 0. So in that case, I can neglect the term which is A2 by A1 square. The velocity of E flux will come equal to just root 2 GH. So is it not the same speed any particle will acquire after falling through high touch because of gravity and starting from rest? Is it not? If I drop a particle from rest under the action of gravity near the surface of the earth, the speed it will acquire after falling through high touch will be root 2 GH only, no? I hope you got this thing easy only. So just a moment, I'll repeat it once. I have selected two cross section. One is cross the free surface of the tank, and I consider that free surface is falling down with speed V1. Other cross section is the cross section just outside the opening where the fluid is coming out with speed V2, and that is exposed to the atmosphere, so their pressure P0. And the pressure just at the free surface is, suppose in general, if it is PT, then we are writing down the Bernoulli principle, conserving those three things at this two cross section. P plus half rho V square plus rho GH will make it equal at both of these two cross section. And we have selected the position of the lower cross section to be the reference. So we can consider this height h is the height of the free surface from the center of the cross section, which is A2. So the gravitational potential energy per unit volume at cross section A2 will be 0. So I'm not writing that term. Another equation I'm using is A1V1 equals to A2V2, since it is incompressible fluid and no storage is happening in between. So I hope all of you understood the speed of efflux. No? Okay, I can take a new page. Okay, I think I can take a new page. Okay, then. Let's suppose if we have got some, let me draw it first. Suppose if it is given, the water is filled up to height h, which is suppose capital H, and we are going to make a opening at a height, suppose small h, and it is told that area of the cross section of the opening is very small as compared to the area of the tank. So in that case, we can consider the speed of efflux to be just root 2 gh. And this container is kept on a horizontal surface. So here the water, whatever will come out, will be going around, going in a parabolic path. And maybe somewhere here, it is going to hit the horizontal. So this is going to be range. And we need to find the range and also what will be the height of the opening so that we can have maximum range also. So that is very simple. The fluid will be coming out with a speed which is going to be root 2 g and h, where h is the height of the opening from the free surface. So height of the opening from the free surface here is going to be capital H minus h. That will be 2g h minus h. And since if I throw a particle, suppose horizontally from some height h, so the time it will take to reach the ground, that root over 2h by g. And for whatever time it was in air, for that time only it was moving in the x direction. So how much it has moved in the x direction in total, that will be our range. So what is going to be our range is, so time of flight, if I write down, is going to be root over 2 small h by g. So range will be the velocity in the x direction into time of flight, and the velocity in the x direction is 2g capital H minus a small h. Time of flight is 2h by g root over. So if you simplify it, it will be 2 times small h into capital H minus small h. I hope you got this thing, everyone. Now, instead of having a opening made at a height h from the bottom surface, instead, suppose what I do, I make the opening at a height depth h from the free surface. Let me draw that figure again. Another figure here, just a second. Now, what I'm doing is, instead of having the opening made at height h, I'm making that opening at a depth h from the free surface. Okay. So what we have is, I'm making that opening at a depth h from the free surface. Everything same only. The free surface is at a height capital H from the horizontal. So again, the fluid will be coming out of this opening and will be hitting here. And we need to know what is going to be the range now. And what you will find, the range will come same. In this case, the time of flight, what is the height above which I am going to throw, or whatever height above which it is going to be projected horizontally, is going to be now capital H minus small h. No? So time of flight, you will find it will be twice of capital H minus small h by g. And now the range again, if I find out by Vx into t, but now the height of the opening from the free surface is our small h. So the speed of efflux will be 2gh, root 2gh, no? Root 2g small h. No? So here what you will find, the range will be root 2g small h into twice of capital H minus small h by g. And what you find, is it not coming same? H into capital H minus small h. So what you find is that For the openings made at same distance from the bottom and the top surface, the range is going to be same. Because if you make a opening at 1 meter from the free surface or 1 meter from the bottom surface, both of these two will be having same range. You can opening at same height. I hope all of you understood this thing. Now next just I'll give you a small homework. Since you know how the range is going to be depending on the small h, the range is going to be our twice of capital H, sorry, small h into capital H minus small h. So to find the maximum range, what I can say here is the range is going to be a function of small h. No? So you apply maximum minima and you find out for what value of the h the range is going to be maximum. I hope all of you understood the question. No? You can apply maximum minima or whatever. We have got, suppose if I'll give you a function is y equals to 2 into 5 into 5 minus x. So you can find dy by dx or whatever way you can figure out for what value of the x this y will be maximum. Same here, no? Capital H is a constant and small h is the variable, like the way here 5 is the constant and x is the variable. So please try that thing and remember that result also. Okay, so two things. One thing I have told already, for the openings made at the same height and the same depth, the range will be same, and you determine that thing on your own as a homework. At what particular height or depth we must make that opening so as to have maximum range. Cover this thing, everyone. Okay, I can take a new page now. Okay, then next we'll see something which is called Magnus effect. Okay. What you will find in playing cricket, the spin ball is more difficult to predict in what path it will go than a fast ball. No? What happens? A spin ball will be spinning as it will be moving forward. Suppose if I have thrown a ball whose center of the mass is moving with VCM, and suppose it rotates with omega. In air it is happening. It's not like rolling that slipping kind of thing. Then if I'll ask you what will be the velocity of the topmost point of the ball will be, it is going to be VCM plus R omega, the velocity of the top point. And the bottom point, if will be having a velocity, so it will be having VCM this side and it will be having R omega backward. No? Now what I have is, suppose if I consider VCM to be more than R omega, then the bottom point V and top point T, the bottom point will have a velocity VB, which will be VCM minus R omega. Now, if I take the top point and bottom point for that, now the thing is, whenever I have a solid moving in a fluid or even a fluid moving, uh, uh, what to say, moving while it is in contact with a solid, so there is always going to be a layer which is just in the vicinity of the solid, which is going to be moving with the solid. So whenever you have a fluid moving past a solid, then the fluid layer, which is going to be just next to the solid surface, will be sticking with the solid surface. It means it will be doing the same exact thing, whatever will be the solid surface doing. The fluid layer that is in contact with the ball at the topmost point will be moving with the velocity of the ball, whatever I have at topmost point. And the fluid layer at the bottom point will be moving with this velocity of the ball, whatever I'll be having at the bottommost point. And for the top point and the bottom point, if I apply Bernoulli, and the height difference is not going to be much. So the height term I will neglect. Since the top point and bottom point are not going to be very far apart, since it is a ball only, so we'll neglect that term. So what we have is pressure at the top, if I write down, plus half rho Vt square must be equal to pressure at the bottom plus half rho Vb square. Now pressure at the top minus pressure at the bottom, just a moment, pressure at the bottom minus pressure at the top is going to become half rho Vt square minus half rho Vb square. And we know the velocity at the top is more than the velocity at the bottom. So this term, half rho Vt square minus half rho Vb square, will be more than 0. So Pb minus Pt must be more than 0. So what we can say, that from below, the pressure that is being exerted on this ball is going to be bigger than the pressure that is exerted on the ball from above. No? So from below, the pressure will be Pb, and from top, the pressure is going to be Pa. And what you are going to find, there will be a net force that will be acting on it, except gravity. Correct. In that case, if at all only gravity was the only force acting on this ball, then what will happen? It will take a projectile path. But now we have got pressure forces resulting into a net force upward. So now the force that will be acting on it in the vertical direction will not be just gravity, will be resultant of this pressure force and gravity, which is not going to be same as gravity. So it will not be taking that projectile path that our brain will predict, and it will deviate from the path. That's why it becomes confusing to play. It becomes tricky to play a spin ball. I hope all of you understood me. In case if our brain will predict that ball will be going in this path, since we are considering that, okay, gravity might be only acting, but instead the ball will end up deviating from its original predicted path. Okay, no. Maybe if YouTube works, I'll show you a video. Then by one YouTube nice it is. Just Magnus effect. See, he's going to throw a ball from Grand Canyon, and one time he throws it without spinning, and it falls in almost the path we predict. But once he gives the spin, you see it will take a path which is going to be way too different. Your Wi-Fi doesn't allow to connect to YouTube, I think so. Just a moment, I'll just change the Wi-Fi connection. Just give me a moment. See, but first he is going to drop the ball without spinning it. So it's going almost vertically down. Correct. In the end, it deviates a little bit because of the wind blowing in there. Okay, no. It almost falls vertically down. Now, this time he has given a spin. And see, instead of going down, it is falling so far ahead or not. Got the video here, no? See, after giving this spin, see how far it is going instead of falling just vertically down. You should know, everyone, this Magnus effect. Here you check out. He has given this spin up before along with the velocity. You can check out this thing later on. I hope you might have understood. Just a moment. Next, next thing that we need to know, it is called aerofoil effect. The wings of the aeroplanes are designed in a manner such that the air above it and below it will not be moving with same speed. Suppose the air above it, it is moving with the speed Vt, and below it is moving with the speed Vb. And somehow we have managed to have a speed above to be bigger and below to be lower. And again, what we'll do, we'll write on P plus half rho V square. And since the height difference is not going to be much, so we'll neglect that. So what all terms I will have? Just the pressure and the velocity term. So P plus half rho V square will be equal to constant. So I'll write down PT, same thing, nothing different. Half rho VT square equals PB plus half rho VB square. So what we get is PT minus PB, or maybe I write down PB minus PT. PB minus PT is going to be half rho VB square minus of half rho VT square. And since VB is less than VT, so PB minus PT is half rho VT square minus half rho VB square. Now VB is going to be less than VT, so PB minus PT will be more than 0. So it is going to experience a net force that is going to be upward. That force is called that lift force, because of which the aeroplane can fly. So all of you understood this thing as well, aerofoil effect. You can copy this thing if you want to copy. Next thing, you might have heard the name also. It is called siphon. If you want to transfer some fluid from one container to another container, what you do, you take a pipe, you suck at one of the end so as to start the flow. And if the fluid is, maybe I'll draw the figure first, just a moment. Suppose we have filled fluid up to this level, and we are going to insert a tube. Whose one end is inside the liquid and the other end is outside. And the other end, whichever is outside, its level is below the, suppose the end which is inside the water is A, and the end B which is outside the end B is having height lower than the height of A or not? So what we have is, again, what I will do, I will consider two cross sections. One will be the cross section where the fluid comes out with suppose speed V just outside the opening. This cross section number 2. And here I'll consider this as our cross section number 1. Maybe I'll take this one as cross section number 1. Okay. Then what we have is, if suppose here the fluid is coming down with speed V1, here it is coming out with speed V2, we'll apply Bernoulli. Both the sides are open to the atmosphere. So at cross section 1 and 2, if I apply the Bernoulli, at 1 pressure is P0, it's moving with speed V1, so half rho V1 square. And suppose the position where I have the cross section B, that is something taken as the reference, then this will be the height h. No? So it's going to be having height rho g h. And next, for the opening B, it is also exposed to the atmosphere, so P naught coming out with speed V2, so half rho V2 square, and there itself we have considered the reference point, so their height will be taken as 0. So P naught gone. And then again, I can write down A1 V1 to be equal to A2 V2. So what we have is A1 V1 to be equal to A2 V2. So this is our equation number 1. This is our equation number 2. From this 2, we can solve for the velocity V2. So P naught gone. Then we have got half rho V1 square plus rho GH equals to half rho V2 square. Now, in case if I have V1, so sorry, A1 to be very, very big than A2, then what if we will find A1 by or A2 by A1 is going to be equal to V1 by V2. No? That means A2 by A1 is going to be way, way too smaller than 1. So V1 by V2 is going to be very much smaller than 1. So V1 will be very, very small than V2. So V1 squared is going to be nearly 0 and we will neglect it. Or we can neglect V1 square with respect to V2 square. So V1 term will be neglected in case if it is given A1 is very much bigger than A2. If nothing told that what is the area of the cross sections are, then you must consider this case only. So considering this approximation, what we get V2 will be root over 2GH, simple like that. So what basically matters is what is the level of the free surfaces from the exit side. No, doesn't matter where we have inserted the other end, as long as it is inside the water, obviously. But the speed at which the liquid will be coming out of the other end will depend upon the height difference of the other end or the exit opening and the free surface. This is something which is called siphon. Okay. So by this, I can say our syllabus for fluid mechanics is over, so that I can start properties of the matter in the next class. So up to properties of the matter only, you will be having things in this exam. SHM will not come. And maybe one more class I will take on Monday or Tuesday. That will be enough. Okay. Okay. Copy this thing in case if you want to copy. I'll take a new page. Please try this question as a homework. One more question I'll give. We'll discuss this question in the class. But before that, please try these two questions.